This is the video presentation for the project that we did for our social network analysis course taught by Dr. Shakti Balan. In the first round, we were supposed to select two data sets from Snap and compute the centrality measures for each of them. So our first data set was Wikipedia Vote Network. A small part of Wikipedia contributors are administrators who are users with access to additional technical features that aid in maintenance. In order for a user to become an administrator, a request for adminship is issued and the Wikipedia community via a public discussion or a vote decides who to promote to adminship. Using the latest complete dump of Wikipedia page edit history, we extracted all administrator election and vote history data. This gave us 2,794 elections with 1,03,663 total votes and 7,066 users participating in elections. Out of these, 1,235 elections resulted in successful promotion, while 1,559 elections did not result in the promotion. About half of the votes in the dataset are by existing admins, while the other half comes from ordinary Wikipedia users. The network contains all Wikipedia voting data from inception of Wikipedia till 2008. Nodes in network represent Wikipedia users and a directed edge from node I to node J represents that user I voted on user J. So clearly this is a directed graph and a dense one. So this is the code. Let me explain it one by one. First we imported all the Python libraries which were required. Second, we created a network X graph for the given data set. From here, we start computing the degree centrality. We start computing the network measures. The first one is degree centrality. The degree centrality for a node is the fraction of node that it is connected to. The average value that we got was 0.001. Second one was eigenvector centrality, which computes the centrality for a node based on the centrality of its neighbors. The average value that we got was 0.004. Then comes Cud centrality, which computes the centrality of a node based on the centrality of its neighbors. It is a generalization of eigenvector centrality. Here we got the average value of 0.02. Then comes PageRank, which computes a ranking of the nodes in the graph G based on the structure of the incoming links. It was originally designed as an algorithm to rank web pages. Average value that we got for PageRank is 0.0005. Then we computed betweenness centrality of a node, which is the sum of fraction of all pairs shortest path that pass through node. The average value that we got was 0.001. Then we computed closeness centrality, which is the reciprocal of the sum of shortest path distances from node to all n-1 other nodes. The average value that we got for closeness centrality is 0.075. Then comes graph transitivity, which is the fraction of all possible triangles present in G. The value that we received was 0.005. Then we computed the clustering coefficient. Now, our second dataset was Astrophysics Collaboration Network, which covers scientific collaborations between authors, papers submitted to astrophysics category. If an author I co-authored a paper with author J, the graph contains an undirected edge from I to J. If the paper is co-authored by K authors, this generates a completely connected subgraph on K nodes. The data covers papers in the period from January 1993 to April 2003. It begins within a few months of the inception of ARXIV. Same as above, first of all we imported all the necessary libraries, then we generated the graph, then we computed all the network measures, like this one is degree centrality, the average value is 0.0004. Next one is eigenvector centrality, for which the average value that we got was 0.001. Then comes cut centrality, for which the average value that we got was 0.016. Then comes page rank, and the average value was 0.0003. Then comes betweenness centrality, whose average value was 6.4772. Then closeness centrality, whose average value was 0.0002. Then we computed the graph transitivity, whose value was 0.0015.
We draw a random graph, a random Erdos Henry graph where n equal to 100, k taken as 2, and so we calculate the probability and we draw the graph using the function g equal to nx dot Erdos underspace Henry underspace graph, np seed here is none and directed is equal to false. Then uh, we calculate the length. We use the length g dot node function, which gives the number of nodes in the graph, which is equal to 100. Then we compute connected components. We draw the connected component as a subgraph using the function gc equal to max nx dot connected underscore component underscore subgraph g key equal to length. Now here we calculate the number of nodes in this connected subgraph, which is 74. So finally we import the numpy library as np. We create the two arrays r and k. Now for now we use k in np dot arrange. Here np dot arrange function, and arrange function is a function in Python which returns an array with evenly spaced element as per the interval. The interval mentioned is half open, that is start to stop. So the value of start is at 0, and interval is between 0.2 and stop value is 5. Now we draw different random graphs, and for that we calculate first the number of nodes in the graph and then number of nodes in the connected subgraph. Then we calculate the ratio of the number of nodes in the connected subgraph divide by the number of nodes in the original graph. We put that value in the R array and the value of k in the corresponding value of k in the k array. Then we print the R function, and then we plot the graph between the k degree of nodes versus the net nx by n, which is the number of nodes in the connected subgraph divided by number of nodes in the original graph. And then we import the matplotlib library as plt, and then we use the following function to plot the graph.
Now we have, for the third round, we will now try to apply the community detection algorithms on the original network that we have formed by on our both of the two datasets that we have chosen. First of all, we'll import all the required libraries, network, and all the required tools that we will be needing while completing the communities in our game graph for our two datasets. First, we'll import network keys as network as NX, and we'll try to include matplot and label. And from operators, we'll include item data. First, we'll try to create and visualize the graph. For that, we'll read the edge list from our given first dataset and we'll draw it. And by using plot.show, we'll get the graph as follows. For the first dataset, we'll get the graph as this. And now for the given graph, we'll try to find out what are the communities that are present. First, we'll try to apply a greedy modularity approach. And what this greedy modularity approach says that it is also called the Lewisian method for community detection, and it extracts the communities for large networks. It is greedy optimization. As for greedy, it means first of all, whenever it finds whenever it first finds a community, it makes size between them and then sort them out. Now, theoretically, this results in the best possible grouping of the nodes of given network. However, it doesn't go through all possible iteration of the groups, so heuristic algorithm is used instead of it. Now, in our code we first list greedy modularity communities as C. Now we'll print the number of communities and the communities. The number of communities we get is 1063, and what we have done is we have also printed all the communities that are formed. So there are total of 106,063 that we have printed over here. Moving ahead, what we'll do next is we'll try to apply the same process for k-cliques. Yeah. Similarly, we'll now apply k-cliques, find out the communities, and for here we'll try to use the clique percolation algorithm that we have learned. Now we'll import network kx at nx and for this, for CPM, we are using k as equals to 2. And first I'll give you the main idea behind it, that we'll first find the cliques and we'll group them together. And if we see that if two cliques have a k plus 1 neighbor as common, like greater than equal to k plus 1, then we'll make an edge between them. For first, we define k cliques community, g cliques equal to none. Cliques is none. We'll find cliques. Cliques is frozen set C for C in cliques. If length of C is greater than equal to 2. Yeah, that's the basic definition of clique. Now next we have membership picked equal to default. First we'll set it to default, and for we'll form for loop, and we'll try to find nodes in the clique. And in the percolation graph that we are forming, we'll first set it to nx graph, and we'll try to add nodes to it. And for our adj underscore key, we'll first make a function that will get adjacent cliques, and it will have two parameters, cliques and membership. So if this is the condition, if length clique dot intersection adjacent clique, that is the adjacent clique has greater than equal to 3, that is 2 plus 1, then we'll add it to our percolation graph. Now connected components of clique graph with percolation edges are the percolated cliques. We'll use the frozen central union, we'll get the union of them. And for our get adjacent cliques, this is the definition of the cake that get adjacent clique that we'll be using to get the cliques that are adjacent. We'll now form the graph, that is h equal to nx graph, and we'll list it and then print. So for example, these are the cliques and that we have formed. For example, if I try to take any, for example here, frozen set u65337, u58243, these are basically two nodes that have been formed as a community, and if any other community has nodes that are equal to k plus 1, that is they are sharing like 3 nodes together, then we'll form a basic edge between them. And in the next we'll try to visualize it and we'll try to create a graph of it. Now so we'll see that we'll try to plot the result that we have got here. So first we'll position the node in the string layer, and we'll draw the nodes by using the parameters as g, position, node color is equal to color. We'll try to for different communities, we'll try to map it by different colors, and the label is equal to false, node size is equal to 5. Plot show, or by using plot.show, we'll print it. So here we get the result as here. We have used different colors to get the different communities, as we can see here. Now we'll try to apply the Greiffman-Newman algorithm. So what this basically does is it detects the communities by progressively removing the edges from the original network. So we'll just try to apply it. Whatever graph that we have got, we'll use count equal to Greiffman-Newman, and we'll get the output as follows. It just generally gives a betweenness indicator. It is an indicator of highly centered nodes in the network. For example, for any node that we have the betweenness is divided the number of shortest paths between the pairs, we'll run through it. Now this extends to the definition of cases of edges. By defining the edge betweenness, it tries to calculate the edge betweenness of a node. What edge betweenness does is that if any of the edge, for example, that then there is an edges AB, and we try to see all the shortest paths containing that edge, and we try to calculate the edge betweenness of it. So next we have, for our next data set, we'll try to find, these are all the result that we get applying the Greiffman-Newman algorithm. So now to apply k-cliques to find out the communities, again we'll try to, by getting all the edge betweenness values, we'll try to apply it and to find out the communities. That's what we have to do in this. So with the same function is used, get adjacent cliques, and if clique intersection of adjacent clique is greater than equal to 3, then we add it to our percolation graph. We'll add that edge and we'll form an edge between them. So these are all the values that we get. All the separated by brackets are the different communities, and in them following by a square bracket we get the nodes in that. Okay, we'll plot it. We'll plot the result of k clique. So by using the position and string.layout, we'll draw it by using the 4 parameters that we have. G is the graph position, node color is equal to color, and map with labels. Plot.show, we'll use plot.show to plot it, and yeah, this is what we get. So now we see we have basically applied it to both of our graphs that we get. That our first one was Wikibot, and what we did is that the basic thing was that we first tried to use the greedy modularity approach to find all the cliques, and then after we got the cliques, we find it by applying the CPM, clique population method, to get the communities and form a CPM graph, clique graph. So what we have learned in the project third is that while analyzing communities, it generally gives us a better sense of understanding the users. And why do we analyze this is that they provide a clear global view of the user, and a community that can be, because communities can be considered as a summary of the whole network, so it's basically easy to visualize it. For example, as you can see here, as this is a very densely knit graph, and if we try to find out like how are these communities sharing something common or not common, these can also be used to reveal some properties without actually revealing some individual's private information. What we see is that it is quite different from clustering that we have studied earlier in our lesson, and so thus we see we'd like to conclude it that this helps us to observe some things, some basic settings that we cannot observe it on individual level. Thank you so much. This is the end of our round key and end of our project. We'd like to conclude. We are very thankful to Sakri sir for teaching us this lesson and providing us with all the basic knowledges. Thank you so much.